Hello. Last day we have discussed some mean, some variance of BPSK. Our main purpose was to calculate the probability of error of BPSK. And we have seen one new thing, that is Gaussian random variable probability density function, which is denoted by this, and the meaning of each variable I have mentioned here. Now for bit 0 and for bit 1. Okay. Now listen, for bit 0, this thing mentioned in this way, where f of capital, the random variable, here f of y, the random variable observation, this is the small one, this is the small y, slash 0. That means for bit 0, the expression is 1 by root of 2 pi sigma square. Sigma means variance. So what is the variance? We know last day, n naught by 2. N naught by 2. What is the mean? Either root of EB or minus root of EB, depending on 1 or 0 bit. So that concept, that value we have to use here, that sigma square, that is your actually variance, that is n naught by 2. Just I'm putting the value, that's all. And x of this small x, instead of it will be y, small y, minus mean. So mean for bit 0 is minus root of EB. So minus minus plus, plus root of EB divided by 2 into sigma square, means n naught by 2. Just I put the values of mean and variance. Then I got this one. Cancel out something. Then finally I am getting this expression, which is actually the probability density function of Gaussian random variable this, when bit 0. Similarly for bit 1, I am not putting all these values, directly I am writing. For bit 0, this is your plus root of EB, here it will be minus, that's all. If I am putting all the values, we will get this one. So I am not doing that. Okay, so these are the probability density function of Gaussian random variable for bit 0, for bit 1 of the observation y at the output of the integrator for BPSK modulation technique at the receiver side. So up to this, I think it's okay. Now, if I am plotting, using some MATLAB coding, if I'm going to plot this one, that means this is equals to this. You can put this, do this plot using MATLAB coding. This equals to this. So for 0, that means bit 0, we are having this kind of something. This kind of something. Similarly, for bit 1, we have this kind of something. So for bit 0, y slash 0, for bit 1, y slash 1 is there. This is one Gaussian, and this I am getting for Gaussian random variable when bit 0 is transmitted. This one I am getting for Gaussian random variable when bit 1 is transmitted. So this portion is for 1, this portion is for bit 0. Now there is some, actually this one, listen very carefully this part. this actually it's like this, which which starts from minus infinity and up to plus infinity. That means this one is going from minus to plus infinity this side. Okay. Similarly, this case, it is like this, up to plus infinity, going like this. So there is some point where these two meet. This is the point where actually zero is present, and this zero is a special zero, which is nothing but threshold. This zero is nothing but threshold. Okay. If the observation value is more than this zero, that is right side, then receiver will think that bit 1 was transmitted. If observation is less than 0, that means left side of this line, observation is less than 0, then receiver will think that bit 0 was transmitted. That is the case. So this 0 is very special 0, which is nothing but threshold. Now, what about this region? What about this region? What about this side, this region? That means I mean to say actually this portion, this portion, this portion very clearly understand actually this portion if I'm showing here. So if it is the line, threshold line 0, more than this bit 1, less than this bit 0, and this curve is for bit 1. So if observation is in this side, then what we will think that bit 0 was transmitted, but actually bit 1 was transmitted, because this curve is for bit 1, but this curve going to the left side and beyond the threshold line, that is this portion, this region. So for this region, receiver will think that it is less than the threshold value, that means 0 was transmitted, but actually 1 was transmitted. That is the wrong decision. That is the probability of error. So how much probability is there for the wrong decision of the receiver? That is the our topic of discussion. How much probability is there that the receiver will think 0 was transmitted, but actually 1 was transmitted? So how much probability of the wrong decision? How much probability of wrong decision by the receiver? That is the part of calculation or topic of discussion. If it is not clear, again I am repeating, this is very important, very important. This is a curve, this is a line. This curve is for bit 1, that means for this line, this vertical line is the threshold line. If the probability density function value is more than threshold value, then receiver will think that 1 was transmitted, and it is correct. But if this region, if I'm talking about this portion, this region, then receiver will think that 0 was transmitted, because this portion probability of density function is less than 0, less than threshold line. So receiver will think that 0 was transmitted, but actually 1 was transmitted. Actually 1 was transmitted. Is it clear, I think? Now? Similarly for this also, if I'm able to draw this part, this one. So suppose threshold line is here. 0 was transmitted. This is the threshold line. This is the threshold line. So receiver will think that 0 was transmitted for this region. But what about this region? This region. This regarding this region, receiver will think that 1 was transmitted because this region probability density function is more than threshold. So receiver will think that 1 was transmitted, but actually 0 was transmitted. So that is the probability of error. So due to, again, I am repeating, due to this, I am getting this one. Due to this, I am getting this one. Okay, and both the curve varies in between minus to plus infinity. Minus to plus infinity. Okay, here somewhere point is there, that is the threshold point. This region is actually for bit 0, but it is more than threshold. So this region is nothing but the probability of error region. Here also the same thing. This region is the probability of error region because in this region actually 1 was transmitted, but this region value is less than threshold value. So receiver will think that 0 was transmitted. That is a wrong decision. So from these two, we got this one and this one. Now, next. This is very important explanation actually. Now the next thing is that here. Now we are assuming some channel, some particular channel that is known as binary symmetry channel. I think you read it in information theory and coding. The subject, there is a channel that is the binary symmetry channel. What is the concept of this channel, BSC channel? That I have written very clearly. Transmitted bit is 1, but receiver decides 0 was transmitted. That is denoted by probability of error for transmitted bit. Transmitted bit is 0, but receiver will decide that 1 was transmitted. So probability of error for transmitted bit. 1 was transmitted, 1 is received. 0 is transmitted, 0 is received. But 1 is transmitted, 0 is received. So that is the probability of error. 1 is transmitted, 0 is received. That is denoted by this one. 0 is transmitted, 1 is received. That is denoted by this one. That is the concept of BSC, binary symmetry channel. 1 is transmitted, 0 is received, denoted by this. 0 is transmitted, 1 is received. That is denoted by this. Or not received actually, decides. It decided by the receiver. Now, what is this? That means 0 is transmitted. But receiver will think that 1 is done. 1 is received. That means receiver makes some wrong decision. Receiver makes some wrong decision. Okay. So it means 0 is transmitted, but receiver think that 1 is transmitted. Okay. So actually this is denoted by which region? Actually transmitted bit is your 0. That means in this region, but wrong decision will be in this portion. So that is your 0 to infinity. This is actually 0 to infinity because this curve is going towards infinity side, in positive infinity. So 0 to infinity, in this range, receiver may did some wrong decision. So this integration limit is very important. Whenever this one, that means whenever this one, 0 is transmitting, but receiver will think that 1 is transmitted, which is wrong. Then we have to follow this region. This region. This region comes from this curve, which is in between 0 to plus infinity. Then it is a wrong decision because more than beyond the threshold value, receiver will think that 1 was transmitted, but actually 0 was transmitted. So limit 0 to positive side plus infinity, this one. This thing just to understand, very, very interesting, but very important also. So this is the case. Then we'll put the value and we'll go for the calculation. Next thing I'm telling here. Meaning of this, actually 1 is transmitting, but receiver will think that 0 is transmitted, which is wrong. So 1 is transmitting means this portion, but receiver makes some wrong decision due to this portion, small portion, which is minus infinity to 0. Is it minus infinity to 0? In between minus infinity to 0, only this portion is there of this curve, okay, which is wrong actually. That is why this kind of limit. Now, minus infinity to 0 and 0 to plus infinity. So actual thing is what? Instead of minus infinity to 0, if I am writing 1 minus 0 to plus infinity, both the same thing. Minus infinity to 0, instead of that, if I am writing 1 minus limit 0 to plus infinity, both the same thing. So that I did here. Minus infinity to 0, that I replaced by 1 minus 0 to plus infinity, same thing. So what you have to understand actually you have to understand this small region of this curve, this side is a small region of this curve. In between these two small region, there is a line, vertical line, which is a threshold line. And both the curve varies from minus infinity to plus infinity. So I think if you understand this one, if you have any doubt, you can ask me. Okay. Now just this is the case. This value we know. Just to put this value, take it out before the integration. Then now this one, this part. Now interesting thing. Z equals to, we are considering this upper e to the power exponential portion. Z equals to this one. Derivative both side. So dz yz, this term is 0. Okay, so somehow we are getting this one. For y, lower limit is 0, upper limit is infinity. For y, lower limit is 0, upper limit is infinity. If I am putting y equals to 0 here, we will get something of z. Y equals to infinity in the same equation, we will get something of z. So now this equation is arranged in this way. Y is replaced by dy is replaced by dz. Dy equals to dz into root of n naught that I have written. Exponential term is now this one. Lower to upper limit is now this one. Lower to upper limit from here. This is class 12 numerical. This is the lower to upper limit. This is the lower to upper limit, which is coming from here, the value of y. Okay. Now, I have now this one. N naught cancel out. Half 2 by root of pi I am taking, just arranging something. This one. Integration, this limit I have written here, e to the power minus z square dz. Why we did these things? Because this portion inside this angle bracket, this portion is nothing but this portion, which is actually definition of error complementary function, ERFC, ERFC x, which is the lower limit of the integration. So instead of writing this whole thing, we can write down ERFC in the bracket lower limit. This one, lower limit. This is the lower limit. Half, half. So now we have this expression, which is actually your this one. Probability of error for actual bit 0. Similarly, in the same way, the next thing also we will do this one. This one. Up to this I told. After that, just we put these values here. Same way we are doing as previous. We have this one. This part is nothing but your ERFC. Lower limit is this, minus is there. That is why minus term is coming here. 1 minus half of, 1 minus half of. Now, one property of ERFC function we are going to use here. The property is this one. ERFC minus x is equals to 2 minus ERFC x. So this term, now it is written as 2 minus ERFC half 2, this minus, this minus. Okay, just instead of this, use this one. X will be replaced by minus, x is actually your root of EB by L naught. This property I am using here. Cancelling out 1, 1. Finally, we have this expression. Probability of error for the actual bit 1. So, average probability of error is nothing but just add and divide by 2. Finally, we have this one, which is the average probability of error of BPSK modulation technique. This is the final one up to this. So, what we have discussed? We have discussed very simple way. We have started from here. Yes, we have started from here. We know this block diagram. YT received, observed. X1 and X2 is nothing but you know these two things. From here, we are calculating mean and variance. Mean and variance. These values. Then there is some Gaussian function. This is the Gaussian function. And capital X is nothing but the capital Y in our case. For bit 0, for bit 1. From these two things, we have this kind of two curve. From this curve, and by setting the limit of the integration, we can calculate the probability of error for 0 and probability of error for 1. And finally, we can do the average. So this is the case today we have discussed. Right? How to calculate the probability of error for BPSK. Same way you can try for any other modulation technique also. Okay, so we have used this expression direct in fourth module, but in second module, how we are going, we have to calculate this one. That I have shown. But in fourth module, directly we are using this one, where I have not mentioned here that EB is the bit energy, N naught is the noise power, ERFC is the error complementary function. That's all. So today I'm stopping here.